Okay, so this time we're interested in actually solving problems about E2 elimination. So if you are wondering more about the theory of how the mechanism works and all that jazz, look at the theory video, but we're going to be mostly working problems. So say we have a substrate like this, and we're doing a reaction with NaOH. What is the E2 product going to be in this reaction? Okay, well the first thing you want to do is you want to identify the potential leaving groups. In this case, our best leaving group is going to be chloride, or chlorine. So for now, we're going to be doing these reactions on haloalkanes, so in general the halogen will always be the best leaving group. The reason why we want to identify the potential leaving groups is because of our next step. So the next thing we will want to do is identify these beta hydrogens. So let's talk about what we mean by that. So let's take a look at this location right here, which is the carbon bearing the leaving group. So we'll call this the site of interest. Okay, so an alpha hydrogen will be a hydrogen directly bonded to site of interest. So if you're paying attention, you'll notice that there is on a wedge one invisible hydrogen here. That is what we'll refer to as an alpha hydrogen. But a beta hydrogen will be on the carbon adjacent to site of interest. So what we're talking about when we mean beta hydrogens are the carbons one off of the site of interest. So that's to the right and to the left adjacently, this guy and this guy. So any CH bonds will be considered beta hydrogens. So these are the beta hydrogens, and this is our leaving group or our site of interest. The reason we're interested in finding these beta hydrogens is, if you remember from last time, the E2 elimination will occur, or begin rather, with the base attack on one of these beta hydrogens. Now it could attack this one, or this one, and that will give slightly different products, but we, for now, will just consider what we will call the Zaitsev product, and we'll talk about that in a bit. So say we're interested in this beta hydrogen over here, and this is our leaving group, so we know after the elimination the double bond will be formed in this region right over here. Okay, so the first step in getting to our products will be drawing the Newman projection with that in mind. So you should be pretty familiar with drawing Newman projections. If you don't know how to do that, go look at the video about drawing Newman projections. So if we draw the Newman projection, it will look like this. So this front-facing carbon right over here, since we're looking at it from left to right, what's on a wedge is this invisible hydrogen will be found on the right-hand side. On the dash, that will be on the left. And over here on the second carbon, this methyl group is on a wedge, so it'll be on the right. And this hydrogen, this beta hydrogen, is on a dash, so it'll be on the left. And the other groups, this will be upward facing, so it'll be like that, and this will be downward facing, so it'll come out like that. All this should be reviewed. Okay, so as we learned last time, E2, let me get that in black. E2 elimination requires, let me spell that right, the beta hydrogen and the leaving group to be anti-periplanar. Now, anti, you should know what that means. It means they're on opposite sides of the molecule, but periplanar you're probably not so familiar with. It just means that they must be located within the same plane. So in this case, we have our Newman projection, and you should remember from a few units ago what anti means in the context of Newman projections. So all that means here is that we're going to rotate this front group over here. This chlorine is going to go over here, this hydrogen will go over here, and the methyl group will go over here. And now you'll notice that our leaving group is anti, or across the Newman projection, from our beta hydrogen. And the reason we care about this is when you do the elimination, when we draw the product, these remaining guys will be on the same side of the double bond. So what I'm talking about is we have the double bond formed here, we know hydrogen and methyl will be on the same side, so that's over here, and we know methyl and this R group will be located on the same side. So our final product will look like this. Okay, and now if you're going to draw the mechanism, you would simply take that molecule that we had at the beginning, and then you take the base, attack that beta hydrogen, which will donate electron density into this region here, forming the pi bond as this sigma bond, the leaving group, breaks. And as a result, you'll simply get the product. Of course, there are other things that will be present here, like the water generated from the deprotonation as well as the Cl-. We don't really care about that right now. But let's talk about why this is our product. So back up here, if you remember, we had our leaving group located here, and we had the option of choosing this beta hydrogen or these beta hydrogens. Okay, so say we did the reaction choosing the beta hydrogens on the left. What would happen is the base would attack here or here. It should really attack here to make sure it's anti-periplanar. Electron density would go here, and this Cl would leave. So the product would look like this. We just formed the double bond here. Now, this double bond over here is attached to one R group. And by R group, I just mean any sort of alkyl substituent. So that's this over here. This double bond is attached to 3 R groups. Right, it's attached to this methyl group, and this R group over here, this alkyl straight chain. So over here, we consider the more substituted double bond to be more stable. So this is the more subbed double bond, which is more stable. And over here, this is the less subbed double bond, which is less stable. The result is that we call our more stable or more substituted double bond the Zaitsev product. And over here we call this the Hoffman or anti-Zaitsev product. And I'll tell you now, E2 favors the Zaitsev product in general. We'll talk a little bit more about what that means in a little bit, but when you have a sterically unhindered base like NaOH, you will try to form the Zaitsev product whenever possible. Now, if you don't have beta hydrogens there, you might be forced to form a less stable or less substituted double bond. Okay, so that's enough information to get you started. Now it's your turn to try and solve one of these problems. So here's your substrate. I'll tell you that your base is NaOH. Pause this video and give this a shot. Okay, I'm going to assume you gave it a try. So remember our initial steps. We want to, 1, sorry about that, no support. So 1, identify leaving group. The reason why we do this step first is that, remember, our site of interest is going to be this carbon. So when we're looking for beta hydrogens, we're going to be looking adjacent to this carbon. So the second step is identify beta hydrogens. So there are beta hydrogens to the left over here, and there are also beta hydrogens located here, and these are invisible. But if you do the elimination, you'll get a double bond here, and that will have 1, 2, 3 R groups. And over here, if we do the elimination, we will get a double bond here, and we'll have 1, 2, 3, 4 R groups. So this location will give the Zaitsev product. So this is the elimination that we're going to do. At this point, you need to draw your Newman projections. That's why I've labeled this 1 and 2. So let's get the Newman projection corresponding to this. And that will look So the methyl group will go to the right, the hydrogen go to the left, the bromine will go to the right, and the methyl will go to the left. And thankfully, you'll notice that the leaving group and the beta hydrogen are already anti-periplanar to each other. So you know that these two will be on the same side of the double bond, and these two will be on the same side of the double bond. So your product will look like this. If you're asked to draw the entire mechanism, it will simply look like so. The deprotonation occurring at the beta hydrogen of interest, that is anti to the leaving group, electron density donating into this region, into this antibonding orbital, which weakens this, and the Br will come off, leading to this elimination product. Alright, take another one. This one I made slightly easier. So take 5 minutes and pause the video and try to do this one. Okay, I'm going to assume you paused the video and gave it a try. So I've already identified your leaving group, and I've already identified your beta hydrogen. Once again, the reason why we chose that as the beta hydrogen of interest is if you do the elimination here, that has 1, 2 R groups, and if we do the beta elimination here, that'll be 1, 2, 3 R groups. So again, in trying to get the Zaitsev or more substituted stable double bond, we will be doing the elimination at this location. So now you've identified your leaving group and your beta hydrogen, drop the Newman protection. So these, the leaving group and the beta hydrogen, in this case, are not anti to each other. So we need to do a bond rotation. I chose to do it for the back carbon this time. So this Br will move over here, this hydrogen will move over here, this group will move over here, leading to this. Now these are anti to each other, so we know that in the final product, these two will be on the same side, and these two will be on the same side. So the resulting product will look like this. And of course, if you want to draw the mechanism, it will look like this. Now if you're a purist, you'll actually do the bond rotation on one of these, so you're implying that you actually have anti-periplanar geometry. Here you'll notice that that's not really what we do, but in spirit I don't really see a difference, as long as you draw the correct product formed from the anti-periplanar arrangement. So again, the base deprotonation happens here, electron density is donated here, into the antibonding orbital located at the back side of the sigma bond, causing this to break, and you get the pi bond formed in the molecule. Okay, so hopefully you're used to that by now. Let's change it up a bit. So let's talk about terp butoxide. So terp butoxide is a favorite sterically hindered base that comes up often in E2 eliminations. So the key here is that a sterically hindered base will push for the anti-Zaitsev or Hoffman product. So every time so far we've been trying to make the Zaitsev product, but with the terp butoxide with a sterically hindered base with all of these alkyl groups making this very bulky, you will instead drive the reaction toward the less substituted double bond. So let's give that a try. Try it on your own first to see if you can actually figure out what's going to happen. So pause the video. Okay, I'm going to assume you give it a try. So again, first things first, identify the leaving group. That's going to be here, so this is the carbon that is of interest. You know you're going to have beta hydrogens here and beta hydrogens here. So as a result, you're going to be looking at this. So now we have beta hydrogens on both adjacent places to the site of interest. We look at the stability of the double bonds that we can form through elimination. So here, if a double bond is going to be here, it's going to be 1, 2, 3 R groups coming off. And if we form the double bond here, it's going to be 1, 2. So this one over here, the 3, will be the Zaitsev product. And if we do the elimination here, this will be the Hoffman product. Now this time, since we're using a sterically hindered base, we are going to want to form the Hoffman product. So if you do that, the mechanism will look like this. the tert oxide will attack one of the beta hydrogens here. Really, because I was lazy, we should have rotated this so it was more anti. This kind of looks like sin. So we should have done a bond rotation so that the hydrogen was over here and we actually got the true geometry, but it doesn't matter so much since I didn't put any wedges or dashes there to begin with. So once the elimination occurs, we will have these two products because of the rotation. So this will be the major product very slightly, and this will be the minor product very slightly. So although this was the Hoffman double bond, you still have the choice of making the trans or the cis isomer here. So it's a little ambiguous which one will actually find an excess if we do the reaction in real life. I would expect the trans to be formed, but you know, the bulkiness of the tert oxide might actually play a role. It might actually even force the cis to be more. So I'm going to say both of them probably exist. I'm going to say that this is probably the major, but I wouldn't be surprised if it actually wasn't. Okay. Let's try this one. So take 2 or 3 minutes and try this one. Pause the video. Okay, let's give this one a look. So our leading group is here, right? And you'll notice that at this location, we don't have any beta hydrogens. But over here, we have actually quite a few. And over here, we actually have quite a few. So the reaction will proceed because the tert oxide actually doesn't play a role here. The only sites that are open for beta elimination are here and here. So the product will simply look like this. And you could arbitrarily choose the other one too. It won't make much of a difference. Well, the geometry looks a little messed up here, so I'll just use this one. Okay. Let's try something even more interesting. Okay, so another key point is when you're doing this on a cyclohexane. So the key point is that antiperiplanar only works when the beta hydrogen and the leaving group are diaxial, which means absolutely nothing to you right now, but I'm going to illustrate it through an example. So say we have this cyclohexane ring, and we have this chlorine substituent here. How do we predict what the E2 product is going to be? Well, the first step is going to be drawing this in a chair. You should know how to do the chairs from previously in the semester, so I'm not going to go over that so much. So this is one chair, and this is the chair flip. In one of these conformations, the CL is axial, and in one of it, the CL is equatorial. What I'll tell you is that an equatorial CL is pretty much unreactive, and that goes up to this key point over here. Antiperiplanar only works when the beta hydrogen and leaving group are diaxial. So your CL, your leaving group, needs to be axial. Then we look around again for the beta hydrogens. Because there's 2 methyl groups over here, there's no beta hydrogens located at this location. But there is a beta hydrogen located axially in space over here. So what that means is that E2 elimination can occur in that location. The mechanism will look like this. Base deprotonation on the beta hydrogen over there, which will cause double bond to form there. And you'll get this in the chair form, and then converting back to line wedge, it will look like that. Okay, so now try this one on your own. Okay, I'm going to assume that you tried this on your own. Again, the first thing we want to do is we'll want to draw the chair conformation of this molecule, and we also want to draw the chair flip. So you'll notice rather obviously that this CL is axial, and locations adjacent, or the beta locations, you have two pretty nice looking axial hydrogens. So if you do the E2 elimination on these two locations, what you'll get is this and this. Okay, but what I'm saying here is that these are minor products. Remember that our base here is t-butoxide, so we want the Hoffman product. These two double bonds are pretty substitutes. This one has 3 alkyl substituents, and this one also has 3 alkyl substituents. I'll tell you there's a third product that can form, and it's pretty tricky to find. So, back when I said the Cl that's equatorial is unreactive, that has one major section, and that's when you have a methyl group geminal to it, or alpha to it, on the same carbon. So if you look at this methyl group, remember that since it's not, well, I'll just show it to you like this. There are CH bonds located here. Because this bond isn't part of the ring, it is able to rotate. So all these CH bonds up here are able to rotate like an umbrella upward in space. So at some point, they are able to get into an anti-periplanar geometry with the leaving group, which allows the E2 elimination to occur, which will give you this product, where you actually have the double bond coming off of the methyl group that was attached to the ring. And this one, you'll notice, only has 2 alkyl groups, 1, 2, so it is a least substituted double bond, and therefore it is a true Hoffman product. Okay, let's see if I have any more. I think I have one more problem. Okay, so pause the video and give this one a go. Okay, I'm going to assume you tried this. So once you draw the chair conformation where the leaving group is axial, you'll notice that right here you have a beta hydrogen that's also axial. It's kind of hard to see here in this picture. Over here, this hydrogen, unfortunately, you can't use because it is equatorial, and in the chair flip, the Br will be equatorial and the hydrogen will be axial. So you can't actually attack the hydrogen that's located here. It's on the same side as the Br. But the one over here is actually axial to the Br. So the base attack could occur here, which will again cause the double bond to form, and the Br to leave, giving you this as your final product.